Welcome to Module 44 in this series of lectures on statistical quality assurance and statistical process improvement. We're in the midst of studying two-way factorial studies and how one can do data analysis for two-way factorial studies. And in this module, we're going to talk about the definition of so-called fitted two-way factorial effects. What we're going to try to do is quantify the insights that were made in the previous module regarding that glass phosphor study in terms of, we're going to put some numbers to it, so to speak. To begin with, we're going to define what are called main effects. And main effects of factors in a factorial study, we're going to define them as row or column average y bars minus the grand average y bar. Okay, so if we take a particular row average and we subtract the grand average, we're going to call that a fitted effect for that level of factor A. We're going to call it a fitted main effect of that level of factor A. If we take a column average response and we subtract the grand average of the cell averages, we're going to call that a so-called fitted main effect of the jth level of factor B. Here's the table of y bars that we've been working with in this glass phosphor example. If we take this average and subtract the grand average, that is, we take 298 or 289.44 and subtract 262.22, we get 27.22, and we're going to call that the fitted main effect of glass 1. Correspondingly, this row average minus the grand average is minus 27.22, and we're going to call that the main effect of glass number 2. If we take column averages and subtract the grand average, we're going to get so-called fitted main effects of factor B at level 1, level 2, and level 3. So we have 27.22 up here minus 27.22. Notice that those two things add to 0. That's a consequence of the way these definitions are made. If one was careful to carry these things out to an infinite number of digits, this plus this plus this would also sum to 0. Fitted effects of A sum to 0, fitted main effects of B sum to 0. The fact that the 27.22 values here are on the whole bigger than these values is an indication, or is a quantification, that on this picture the gap between glass number 1 and glass number 2 is a lot larger than the change as I go from phosphor 1, say, to an average of these two values for phosphor 2 to the average of the two phosphor 3 y bars. That is, this pattern of up and down, these gaps are nowhere near as large as those gaps. The fact that A number 1, or the fitted effect of glass number 1, is positive says that this profile is above that profile. Glass number 2 has a negative fitted main effect, and the fact that the fitted effect for phosphor number 2 is positive and the other two are negative is consistent with the fact that these guys are bigger than their corresponding Y bars in their for their particular glasses. So I've already said that it's no accident that A main effects add to 0, B main effects add to 0. It's a consequence of how these things are defined. Now, in some cases, if one takes the fitted main effects in a two-way factorial study, they pretty much, together with the overall mean response, capture the entire story that's told in the data set. And what that means is that cell averages are approximately some overall average plus the corresponding A main effect plus the corresponding B main effect. That is, in this particular case, the phosphor response in row I, column J, is approximately the grand average plus the A main effect plus the B main effect, the glass main effect plus the phosphor main effect. The glass phosphor example is in fact one of these cases where there's this approximate equality. And you can see that if I give you again the table of Y bars, and I also make a table of grand average plus A effect plus B effect. So for example, this number right here is grand average plus A number 1 plus B number 1, and the point is that I get back to something that's fairly close to 285. I get to 287.22. And in fact, if I compare this table with that table a cell at a time, they're very much alike, and that is a quantification of the fact that the interaction plot for this particular example is has very much nearly parallel traces. So let's see if I can find that. So the point is that this trace is very nearly parallel to that trace, and that's quantified by this table looking like that table. Well, how can one then make some numbers that say that? What one might do is take the values in this table and a cell at a time subtract values in that table and say, well, those numbers are small, give them a name. In fact, we're going to call them fitted interactions. So we're going to take the average, or take an average for a cell and subtract a grand average plus an A main effect plus a B main effect, and call that difference between, well, that is the difference between what's observed at level I of factor A and level J of factor B, and what we can account for in terms of the factor A, the overall mean, the factor A level I main effect, and the factor B level J main effect. So this thing is confusion for it was supposed to say panel 4 here. These cell-by-cell differences in this particular example are small. They're like 2.22, 1.11 with plus or minus signs on them. And so, for example, if you take this 285 and subtract 287.22, one gets minus 2.22, and that's the main effect. Sorry, that's the two-factor interaction for level 1 of A and level 1 of B, glass number 1 and phosphor number 1. These fitted interactions are smaller in absolute value than the fitted main effects for either factor A or factor B in this particular example. And basically that says that the lack of parallelism on that interaction plot is really fairly small. It's also the case that if you add the numbers in this table up, if you add up all of the AB IJs, they sum to 0. That is a consequence of how these things are defined. We'll come back in the next module and talk about essentially determining whether these various effects are clearly bigger than noise. That is, we're going to make confidence limits on these things. We're going to add margins of errors to these quantities.